All right, thank you very much. It's great to be out of prison, Australia. They dropped the border controls earlier this year, but for 2 years we were pretty much on lockdown with the rest of the world. So it's great to be back in North America. All right, this is a nuts and bolts talk. I'm an experimental physicist, so I've got two of my favorite quotes up here. The upper one is the entirety of the Caltech 1996 commencement speech. He was drafted into being the commencement speaker after the actual one dropped out. Very memorable. And the other one is a quote from Dan Kleppner from grad school. The universe is a surprisingly benevolent place, particularly if you're an experimental physicist working in atomic physics. So this is what I call my NASCAR slide. So these are all the people that have given us money over the years. And here are all the people that have provided help along the way. Okay, so right now I'm a trapped ion quantum physicist. Stealing here from Reiner, Blatt, and Weinland, because if you're going to steal, you might as well steal from the best. To give a little bit of an overview, we have traps in a linear ion trap. We generate these crystals. The spacing here is typically on the order of a few microns. Trapped ions are a great system for doing quantum computing. We've got these things in a harmonic trap, and we can set up these nice two-level systems both internally and externally, and we can apply different sorts of laser control to get coupling between the different ions. Ytterbium, how many people here are ytterbium ion trappers? I'm guessing none. Hence why we have the slide. So we've got ourselves a nice cycling transition here at 370 nanometers, just on the edge where you can buy cheap lasers. We've got various other transitions to metastable states over here, one of which is it's estimated to be up to 6 years in a lifetime. So this guy will last a good long time. These two D states are on the order of milliseconds. There's a state here which is in the spectroscopy tables, should be about 8 seconds, hasn't actually ever been probed, but very conveniently is at a wavelength near that 370 if anybody's interested in playing Hunt the Wumpus with me. We have not found this. We've looked a little bit, but yeah, hard. It's a narrow transition. So this is sort of the rules of the road. And so how do we implement 2 qubit gates? So this is sort of your essential building block, the transistor of the quantum computing. So you've got your 2 ions, and typically what you do is you'd use that nice harmonic trap as a motional bus to generate entangling gates. So you take and map your qubit from ion 1 into the motional modes, and then you run a C0 gate between that motional mode and ion number 2, and then map things back onto ion number 1, and you've got your C0 gate. So this is fantastic. People have been doing this at this point for pushing 2 decades. Except Goldie would like to intervene and ask, what about scalability? Vibrational gates are slow. This is a huge problem if you want to build up large-scale quantum computing. They're very much limited by the secular frequencies or the confinement frequencies of those ions. You're using this vibrational bus, and you've got to do operations on that. So you're necessarily going to be slow. You could think about, oh, we'll just trap harder. That turns out to be quite challenging. You need to increase the trap voltages. As you increase the trap voltage, the chance that you get electrical discharge and you get breakdown in your trap is higher and higher. If you have an old school trap with, say, metal rods, this means you get a little bit of sparking inside of your vacuum chamber, and it's slightly annoying. If you've just invested thousands or tens or hundreds of thousands of dollars in fabricating some very nice piece of microfabricated wonder, and you crank up the voltage a little bit too high, this breakdown voltage thing gets a heck of a lot more sad. So experimentalists generally aren't super eager to be cranking up their trap voltages beyond spec. The first chip trap that was built was fabricated down in Sandia and implemented up in Weinland Lab in Colorado. The fabrication guys didn't understand the typical voltages that they ran a trap on, and NIST proceeded to create the world's most expensive light bulb as a result. So this is a big problem. I've got some ideas for beating this involving things like liquid gallium electrodes. If you are a material scientist or know a material scientist that's familiar with that sort of technologies, love to have a chat. Might be able to pick up a couple of orders of magnitude here, but this has basically been at a standstill for roughly about the past 20 years. So whether or not there's the money and motivation to try to push this, don't know. But even then, it's still not going to solve your scalability problem. You want traps that can go, or gates that can go as fast as your wallet can afford. So I mean, typically these vibrational gates are implemented either with Momo or Sorensen if you're, actually wanting to do things, or Strack-Zoller if you're a theorist and want to play with things that are easier. And it gets worse because as you add more ions, everything gets slower. The mode complexity gets harder. You need to address one of these vibrational modes and things start to get crowded. And that's for one ion. That's the vibrational spectrum for one ion there. As you add more, you get more cross coupling. So you get, omega Z 1 plus 2. This gets challenging. So, and everything's also sensitive to temperature and noise. So to quote the Carney call from the Minnesota State Fair, do you want to go faster? Yes, you want to go faster. And fortunately, there's a solution to this from 2003. So this gives you orders of magnitude faster than the trap period. It's insensitive to temperature. You don't even need to be trapping the ions that hard. It's relatively invariant to the trapping conditions. And it essentially takes away your speed limit for implementing quantum gates. And the way you do this is you need a strong optical force. You're doing things coherently and you're doing things directly onto the atoms. And so if we take a laser pulse and we shine it onto an ion, we get a absorption, we get a kick in a particular direction. And then if we come at it from the opposite direction and we run that same pulse, we can get stimulated emission. And if we structure our pulse so that they're a pi pulse, we get coherent population transfer from the ground state up to an excited state of our choice. We can be assured that we're getting a 2 h bar k momentum kick. So there's a couple different ways to do this. We can use I would say a square pulse. This has got a much lower power requirement, but it's much more sensitive to noise in your power and detuning. So if you're a little bit low on the power, you don't get quite up to pi. If you're a little bit high, you also overshoot a little bit. And if your frequency detuning is off, you're more sensitive to not getting up to your excited state cleanly. You can use a chirp pulse. This has been used very, very successfully, first in the NMR community and elsewhere, to more cleanly get you up into the excited state. This has got the disadvantages of you need more power, you get higher fidelity, and you get less sensitivity to your detuning. So you can't have it all. But the overall point here is if you apply more laser power, you can get faster pulses, so you can get higher rep rates, you can get shorter pulses. You can run this process essentially arbitrarily fast. And I say arbitrarily fast with a little star, because eventually if you throw enough laser power at an atom, other stuff is going to start happening. And I've got an interest in that as well. There's a whole bunch of atomic physics, and in that case you might care about whether you're choosing barium or ytterbium or beryllium for your atom. And it's sort of a little bit of an unexplored area because essentially people haven't tried to fry their ions hard enough. This somewhat gets into, again, with a chip trap. You just spent a lot of money on your chip trap. You don't necessarily want to be throwing many, many, many watts of pulse laser power at that without really knowing what you're doing. Of course, maybe you're a billion-dollar startup and you're perfectly fine throwing away $100,000 chips for exploratory stuff. Okay, so we've got our strong force dependence, or we've got our strong optical force. To make a gate, we need to be dependent on what qubit state we're in. So we are starting off by doing things using Zeeman qubits. So this is a little bit different than the other qubits you may have encountered. Typically, you want something with low magnetic field sensitivity, so you've got good decoherence. In this case, we want something where we can use polarization to either get our 2 h bar kicks or to not get our h bar kicks. So this comes at the cost of enhanced decoherence sensitivity. You throw in a microwave pulse, you can get yourself back to your qubit states quite nicely. So we're not too worried about this in terms of, we're just interested in doing a proof of concept on this. So why can't we use our good old fashioned hyperfine split qubits? Our laser has got a bandwidth of about 400 gigahertz. Again, we want to have these short pulses. The hyperfine splitting in ytterbium is 12.6 gigahertz. This is fairly typical for atomic systems. Rubidium, which we've heard quite a bit about, is 6.8. Mercury, if you're feeling really ambitious, is about 40 gigahertz. So for fast pulses, you're always going to be completely blurring both your excited and your ground state hyperfine structures. So you need something else. Now, if you've got an optical qubit, that's many, many, many terahertz away. That's perfectly fine. You can do that. So that's got good selectivity, but that's harder technical because you've got to implement an optical qubit, and they're also a little bit temperamental for other reasons. Okay, so again, I'm an experimentalist. This is what the actual system looks like. We've got our chip trap, or we've got our needle trap in the middle here because we're throwing about 80 milliwatts of UV at it. This is what the optical table used to look like, and it is significantly more populated now. So experimentally, we want to send a couple of beams in front and back to our ions. We've got auxiliary lasers here. In practice, things are a lot more complicated, and this is actually emitting a huge amount of the other stuff that's going on in terms of beam diagnostics. So we need our pulses. And we want pulses that are resonant with our ytterbium ion, which is at 370 nanometers. You can't just go up to Coherent or Spectrophysics and say, hey, I want a laser that gives me 2 picosecond pulses with a 300 megahertz rep rate, or something fast in the near UV. So we've got to build this up ourselves. The downside of that is that the system gets rather complicated in terms of we start off with a fiber laser, we amplify that up. We do some supercontinuum stuff, so we can actually access pretty much any wavelength we want from here between 1 and 2 microns. We pick off, do some shaping and amplification, and then proceed to do third harmonic generation through a 2-step process. So there's lots of different elements in here. And this was a full PhD thesis to develop. If you want to be developing lasers for a particular atom, you have this complexity of actually sourcing the laser. Again, this is a technological hurdle. You throw enough money at it, it's not a problem. But for starting out, it's a little bit more challenging. If you want to work in rubidium at 80 megahertz, you can get a solution. If you want to work in ions, it's a little more challenging. Okay, so we want to know what we're actually throwing at our atoms. And so we did some pulse characterization. UV is a little bit more challenging. If you've got an IR laser, you can just buy something called a frog. It tells you everything you want to know about your pulse. In the UV, you can't. However, there's a great trick with a Michelson interferometer, which will actually give you an approximation of the pulse width, which we measured about 2.2 picoseconds. We actually checked that with a different nonlinear technique, came out with roughly the same number. The Michelson's way faster to implement. We also have got a very high resolution spectrometer in the UV, about 2 gigahertz for doing other stuff that we use to take pictures of our spectrum. The detuning control is a little bit challenging because we have all these different stages, and because there's a lot of nonlinearity in there. Little changes to crystal temperatures and things like that will send our detuning pushing around. And you think, oh, like you're 400 gigahertz wide, and your hyperfine structures are on the order of a few tens of gigahertz, you should be fine. Well, it actually turns out you're not fine. You need to get that detuning quite accurate, even though you've got a fairly broad window in order to get good pi pulses. So we added some temperature control to our some of the gratings that set the wavelength, and we tweaked up the nonlinear crystal parameters a bit. The student that's currently on this project, Kenji, is currently working on machine learning stuff to be able to actively control the detuning. So it is a gigantic cross-coupled mess. If we take the Fourier transform of our spectrum, we see that that implies that we should have about a picosecond pulse length, and we've got 2.2. We're not sure how much of that is that we're transform limited versus the approximations of Gaussian versus different sort of pulse shapes. But we think we're reasonably close. Other technological problems. So these are sort of like all the, if you're a theorist, it's like, why do I care? Well, these are the things that might prevent an experimentalist from actually implementing your brilliant plan. And so it may be helpful to consider that. We can kind of generate arbitrary pulse patterns. And when I say kind of, we have the technical limitation of a high power ytterbium amplifier. So the ytterbium amplifier is great in that its sort of characteristic response time is about on the order of a millisecond. So if you're talking about things on the order of microseconds, it doesn't care. If you don't feed it a couple milliwatts of power on the order of a millisecond, it gets kind of grumpy and decides to eat itself. That's expensive. We've had to send this back for repair. The second time IPG said, we're not fixing this anymore. It's right on the edge of what we can do, and you're not worth it because we can make money elsewhere. So we're a little sensitive about our fiber amplifier. So what you can do is you can switch things very efficiently and very effectively and very quickly with an EOM and the IR. The problem is that when you run your Pulse protocol, you then have to leave it on for a while to make sure your amplifier doesn't eat itself. And so then you need another modulator in the UV, and sadly, because it's the UV, they're slower. In this case, it's an AOM, and that'll turn on instead of on the order of kind of nanosecond, sub-nanosecond is going to take tens to hundreds of nanoseconds. So you've got to integrate these things together to be able to get the Pulse protocols that we happen to want. Okay, so you combine all this and everything's working, the stars and moon are aligned, and you've got the Coriolis force working for you in the correct direction because you're in the southern hemisphere, and you actually take some data. And what we see is as we increase the power, which is to say as we increase the pulse area, we get pretty darn near 94% population transfer. Yes, okay. Which is fantastic considering that we're still detuned by about 30 gigahertz from the optimal point. So again, we're within 10% of that window. So we're pretty well centered, but we're still not on top. And we've got our theoretical curve there. That's about where we think we should be able to get. And then to check ourselves, we push the detuning off by about 200 gigahertz, so roughly half the width of our pulse. And you can see that, okay, we only get about 42% population transfer. So this is the base fundamental step for being able to implement one of these fast gates. And this is doing it as a single pulse. We don't have to have anything terribly complicated in our Pulse protocol, and we can make it go as fast as we want, given enough money to make faster lasers with shorter pulses and higher rep rates. And this was all in an applied physics letter from late last year. Okay, but I've been talking about strong forces. What about the force? So as a diagnostic technique, prior to this, we had developed the ability to measure very, very small forces, because even though it's a strong force, it's being applied to an atom, so it's globally a smaller force. And fortunately, we have fantastic optical imaging due to our work developing high-NA diffraction-limited Fresnel lenses. So we can take very, very good pictures of where our atom's located within centroids of less than a nanometer. So we've got super resolution capability. And we use that in conjunction with CSIRO to build a 3D force sensor. So we apply a force to our ion, it moves its location a little bit, and that image will get displaced. If we make this out of focus, the spot will get larger or smaller in size, so we can pick up three-dimensional imaging. We do this, we turn our laser power up and down just on a CW laser. This is microwatts, not the 80 milliwatts of pulse stuff. And we can see our ion, very conveniently displaced by the order of a few tens of nanometers. So this corresponds to zeptonewtons of force. It's a very small force. This is equivalent to the gravitational force between somebody sitting in Brisbane up here and somebody sitting down in Tasmania, so roughly half the distance across Australia. So when we've got the full force that our system can provide, we should be able to watch things shift by several hundred nanometers, so it should be visible on screen. However, we have not yet gotten to that point. COVID has thrown a little bit of a ringer into things like supply chains, which is particularly impactful in Australia, where you can't get 4 labs the next day. All right, and here's the team. I should be roughly at time. So that's my story.